Thanks for joining me in today's lesson. In this tutorial, we will be able to calculate standard deviation and z-scores and be able to use z-scores to compare two sets of data. So we are still in section 11.3 in the next little bit of it, and we're talking about z-scores and standard deviation this time. We're still talking about our normal distribution curve, and our normal distribution curve will still look like this, and I'd like to just review a little bit and label our stuff. Right down here in the middle is our mean or our mu. Sometimes we call it with the little x with a hat on it, or x bar. When we jump up one standard deviation, that would be mu plus sigma. When we jump up two standard deviations, that's mu plus 2 sigma, and three standard deviations, mu plus 3 sigma. If we're adding standard deviation, we're going upward above the mean. If we start subtracting them, then of course we're subtracting sigma and we're getting lower than the mean. So we've got mu minus 2 sigma here and mu minus 3 sigma here. Our empirical rule that we learned in a previous tutorial was 68%, 95%, 99.7%. That's the rule that we're remembering for empirical rules. 68, 95, 99, 7. What we do is we divide our normal curve into all of the regions, and we figure out what percent of our data is in each one of these regions. The 68% is within one standard deviation. So split evenly, we have 34% here and 34% here. Within two standard deviations, that's where 95% of the data is, which is an additional 27%. So cut evenly would be 13.5% and 13.5%. Within three standard deviations, either 3 above the mean or 3 below the mean, that's where 99.7% of our data will be, basically all of our data. So there's an extra 4.7% that we're getting, and divided in half is our 2.35% region and the other 2.35% region. There is still that extra 0.3%, which if we cut in half is the 0.15% way up here and the 0.15% way down here. So now we have every percentage of the data for every one of our regions. Today we're possibly going to see some unusual data. And what I mean by unusual data is any data that happens to be more than 2 standard deviations away. This is considered unusual, statistically unusual data, or lower than 2 standard deviations away from the mean. So this would be considered unusual data as well. So anything that's lower than 2 standard deviations from the mean or greater than 2 standard deviations from the mean is considered unusual. You can see that there's 2.5% of unusual data up here and 2.5% of unusual data down here. So that's just a quick review of what we learned in a previous tutorial about our normal curve and each of the percentages in these regions. Today we're going to be calculating z-scores and standard deviation. First, I'd like to show you how to calculate our standard deviation on our calculator. So if you don't already have your calculator, why don't you hit pause and go get your calculator. Example 1, find the standard deviation, which is this sigma, for the following set of data, and here's our data. So what we need to do is, obviously we need to push on first, because nothing's going to happen if you don't push on. Okay, so let's turn it on, and then we're going to go to stat and push 1. So when we go to stat and push 1, we've already done this before, we're going to enter all of our data in. So why don't you go ahead and put in the data. I'm going to pause right now and do it myself. Okay, great. So here's all of our data, and I've already double checked my data. Hopefully you have done that as well. So we've done that. We've entered all of our data into list 1. Now we're going to press stat, and we're going to scroll over to the calculate, And we're going to hit 1 again, which is one variable stats or statistics. And it says that all the data is in list 1, and we're going to go down to our calculate, and we're going to calculate. And this calculates all of our one variable statistics. So what our screen now looks like is right here. And what's important, well, there are a couple things that are important. It gives us our mean. Now this calculator calls it with the X with the hat, the X bar. That's 10.222, looks like 2 repeating. And the other important information that we have here is our sigma. It says sigma of X. That's our standard deviation, 3.938 if we round that. So that's how you can calculate standard deviation given some data points. So now let's talk about z-scores. It says the z-score of a particular data point is the measure of how many standard deviations that point is away from the mean. So obviously on our normal curve, we know that 1.0 is one of the z-scores and 2.0 is another one because this is exactly 2.0 standard deviations away from the mean. But what about 1.5 standard deviations? That z-score would be around about right here. Or what about 0.6 for a z-score? That would be here. What about negative z-scores? Negative z-scores would be below the mean. So a z-score is when we're kind of in between standard deviations. So example 2, it says if a data point is 2.5 standard deviations above the mean, then what would its z-score be? Well, since we're above the mean, I know that it's positive, and obviously 2.5 is 2.5. So 2.5 standard deviations above the mean would have a z-score of 2.5. And in this case, what value would that be for the data above? So what we need to do is we need to take our mean and add 2.5 standard deviations. Well, we've already calculated what our mean is. Our mean up here is 10.222. I'll just round to 3 decimal places. 10.222 plus 2.5 times our standard deviation, and that was the 3.938. So if we plug all of that in, we will get a value of 20.067. This is the data point for this set of data that would be exactly 2.5 standard deviations above our mean. Let's look at example 3. This time, if a data point is 1.5 standard deviations below the mean, then what would its z-score be? Well, if we're below the mean, that means that our z-score is negative, and of course 1.5 is 1.5. So 1.5 units below the mean would be negative 1.5 for the z-score. And if we wanted to calculate what that data value would be, we would take our mean, we would subtract 1.5 standard deviations. So again, our mean was 10.222, and we're subtracting 1.5 times our standard deviation that we calculated on the calculator. And when we plug that into the calculator, we get a data value, a data point of 4.315. That's the value that would be 1.5 standard deviations below our mean. So now let's use our formula to be able to calculate a z-score. A z-score is a way of comparing data sets that may not be easy to compare. We are able to compare apples to oranges in this case. A z-score will measure how many standard deviations a data point is away from the mean of that data set. And here is the formula. This formula will be given to you on the SOL. A z-score will always be x minus mu divided by sigma. Now x is your data point. Mu is our mean. That's our average. Calculator can calculate that. And sigma is our standard deviation. Again, the calculator can calculate that if it's not already given. Sometimes they just give these two values in the problem. So these are the three things we'll be plugging into our z-score formula to calculate. We already talked about this, that a data point is said to be statistically unusual if its z-score is less than negative 2.0 or greater than positive 2.0. more than 2 standard deviations away from the mean on either side. So example 4 is calculating z-scores for a bunch of things. Now they're giving us the mean. The mean of this set of data is 45 feet, and the standard deviation for this data is 10 feet. We want to know what's the z-score for this first data point, 55 feet. Okay, so we're really just plugging into a formula. The z-score will always be the x value, which is 55, minus our mean, which is 45, divided by our standard deviation, which is 10. And in this case, if you plug that into your calculator, if you're going to plug it all into your calculator, I insist on putting parentheses so that the calculator knows what the numerator is. This is not too bad. I can do this in my head. The numerator, I get 10. Divided by 10, I get 1. And I'm going to put 1.0. That's the z-score. That is above the mean. Exactly 1 standard deviation. Let's look at our second data point, 30 feet. Okay, let's calculate that. The z-score will be our data point, 30, minus our mu, our mean, 45, divided by our standard deviation of 10. And in this case, when you plug that in, again, make sure you have parentheses if you're going to plug it in the calculator. I can see that this is negative 15 divided by 10, which is negative 1.5. So this would be 1.5 standard deviations below the mean, below the average. And let's look at our last one, 22.45 feet. Okay, same thing, same formula. 22.45 is our data point. We're going to subtract our mean of 45, and we're going to divide by 10. So our z-score in this case, put parentheses around the numerator, plug this into your calculator, you get negative 2.55. Now what's interesting about this piece of data is since it has a z-score of negative 2.55, since that is something less than negative 2.0, we would consider this to be an unusual piece of data. An unusual piece of data because its z-score is lower than negative 2. So now that we can calculate z-scores, let's look at an example where we have to kind of go backwards. This one, example 5, you have a normal distribution, which is always important to note that we have that. The mean is given to us, the standard deviation is given to us. Which data point has a z-score of negative 3.45? So this time the z-score is given to me and we're trying to find out the data point that has that z-score. So let's write down our z-score formula. We know that z equals x minus mu divided by sigma, and let's plug in what we know. We know the z-score this time, negative 3.45, so I'll put that right here. We don't know the x value. We don't know our data point, so I'll just leave that as x. We know our mu, our mean is 235.7. And we know our sigma, our standard deviation, 41.58. So we can still plug into the formula. This one's a little bit trickier because now we have to solve for this x value. But that's okay. This is just an equation. Don't get freaked out by all the decimal points. That's fine. We're just trying to get rid of this fraction first, so I'll probably multiply by 41.58. I'll do that to both sides. That's one way to get rid of our fraction here. This x minus 235.7, I'll just drop on down. And if you don't mind, this product I will put on the other side, since I like my variable to be on the left side. We should get negative 143.451. We're still solving for x, so let me add my 235.7. I'll do that to both sides, of course. And it looks like we're going to have a data point that is 92.249. So that's not too bad. We just have a little bit more work to do. So this is just a formula. You can plug in any parts that you know and solve for the missing piece. We have one last example to look at in this tutorial, and here it is. It says, suppose your friend receives an 80% on a test in AP World History and a 90% on a test in underwater basket weaving. I didn't know we had that class here. The average score on the AP World History test was 72%. Remember that average is your mu, your mean. with a standard deviation of 6.5%. The average score on the underwater basket weaving test is 88% with a standard deviation of 3%. Statistically speaking, now let's talk a little bit about this. Obviously, your friend might be very excited to get a 90% because that's an A. Maybe they're very excited to get an 80% because that's a B and they are struggling in that class. I understand that there's other reasons to be happy about these grades. I'm just talking statistically right now, Z-score wise, statistically speaking, with which test score should your friend be happier and why? So these are two different classes, clearly. One is an AP World History class, and the other one is a fictitious class that I just made up, Underwater Basket Weaving. They are completely different classes, but we're able to compare these two classes if we can standardize things and look at Z-scores. So what I'd like to do is look at the Z-score for the AP World History. So I'll put AP World History stuff over here. AP World History. So let's look at the Z-score for that. The Z-score would be our data point, which let's see what she got on the AP World History test, an 80. So that's our data point here. She got an 80, or he, I don't know who your friend is. 80 minus, I need our average. So for the AP World History, let's see, the average score on the AP World History was 72. So 80 minus 72 divided by, I need the standard deviation. It says the standard deviation of that test was 6.5%. So if I plug this into our calculator, of course, noting our parentheses there, we get a z-score of 1.231. Now, obviously, this is very good because this is above the average. In fact, it's even more than one standard deviation above the average. So this is a pretty good test score. But let's see how well she did on the basket weaving. So I'll put basket stuff over here, I guess. And let's calculate that z-score. What did she get? She got a 90% on the test here, so that's our data point. We're going to take away the average. It says the average score on the underwater basket weaving test is 88%. So again, she did better than the average with a standard deviation of 3%. So I'll put the 3 right there. Plug this into your calculator, watch out for the parentheses, and this time our z-score is 0.66, and actually it keeps going, I'll just round to the third decimal point, 667. Again, this is good too because this is above the average, but if we're talking statistically speaking, with which test score should she be happier? Well, it's clear, hopefully, that this z-score is better. This one is higher above the average. They're both above average, so that's good in both classes, but since this is higher above the average, the AP test wins. AP World History test score is higher above the average. So the AP test score will win. She should be happier. She should be happy with both scores, of course, because she did better than the average, but she should be happier with the score that's more above the average because this z-score is larger, farther above the mean than this z-score. Thanks for watching this tutorial on z-scores. Let's practice in the calculator and make sure we understand how to compare our sets of data. I'll see you in class. See ya.